So it's a real pleasure to have Lindsey Bleem with us today. Lindsey is coming to us from Argonne National Lab, and she originated her PhD at the University of Chicago. She's very involved in CITA telescopes, as you can tell from her lovely title slide. She's going to tell us about all the nice cluster cosmology you can do.
Thanks a lot. Thank you for the invitation. I'm very excited to tell you, like Laura said, everything we're doing with cluster cosmology with the South Pole Telescope. So I wanted to give you a brief whirlwind introduction to cluster cosmology because I'm sure everyone in the room is not so familiar with the field. So I just wanted to point out that we're really at an exciting age in cosmology where we have all these wonderful probes of the universe, from the cosmic microwave background, the distribution of galaxies, exploding stars that can be used as standard candles, and they're all telling us one generally consistent picture. That we live in a universe whose energy density is not dominated by ordinary matter like you or me. Instead, it's dominated by dark matter, roughly a quarter, and then the vast majority is dominated by dark energy. This mysterious substance, which we have no idea what it actually is. It could just be simply we require a modification to Einstein's theory of relativity. It could be that the theorists are 120 orders of magnitude off in what they expect the vacuum energy to be. But it's really a great puzzle and a bit frustrating as a physicist to know that I don't know what 3/4 of our universe actually is made of. And so in order to solve this, what we want to do is we want to take all the tools in our cosmological toolkit and throw them at it to get many different probes to try to get a handle on what dark energy actually is. And the tool which I choose to work with is clusters of galaxies. Clusters of galaxies are the largest gravitationally bound systems in the universe, masses of something like 10 to the 14 to 10 to the 15 times the mass of the sun. And as the largest gravitationally bound systems, they are extremely sensitive to things that affect the growth of structure. And that's shown in this figure here. This is a picture of what people thought the universe was in order 1990. We lived in a matter-dominated universe, no dark energy. Here at Redshift 0 in the local universe, this is a picture of the distribution of these wonderful galaxies. Here's an optical picture of a cluster of galaxies. And as you go further back in time, there are less and less clusters because clusters take time to grow. It's higher structure formation. Now, if we instead contrast this picture to the universe we believe we live in today, based on all of these observational evidence from this wide range of probes, what you see instead is this, the same distribution of galaxies in the local universe. But as you look further back into the distant past, there are more and more clusters because in the dark energy model, clusters grow slower. And so in order to see the energy, the abundance of clusters we see today, they had to start forming sooner. If we quantify this a little bit, and now we ask what is the abundance of clusters as a function of redshift, for a few different values of the dark energy equation of state, we see that probing back into the past at higher redshift produces progressively different predicted numbers of clusters that we should see. The abundance of clusters depends on the matter-power spectrum, the lumpiness of matter, this growth of structure, and at lower redshifts we can see this rate of expansion, this volume effect. So this is a model. This really motivates why you do clusters for cosmology. You want to look back in the past and essentially count clusters. Cluster cosmology, at its simplest, is a counting experiment. We need to do two things. We need to find all the clusters we can, and we need to understand what we found, and then we need to weigh them. We need some way to connect this observable of the universe. Whether we're counting the number of galaxies, where we're measuring the gas properties of the clusters, we need to connect it to the overall mass of the system, because it's through this mass that we connect things to our cosmological models via simulations. And historically, there's three approaches to doing cluster cosmology. Optical surveys, finding overdensities of galaxies in the universe, is how they got their name. X-ray surveys, clusters are incredibly bright, extended sources of X-ray emission on the sky. And finally, the newest player on this scene, the reason why me, as a cosmic wave background experimentalist, is talking to you, SC cluster surveys. And they each have different trade-offs. So optical surveys are wonderful. They find clusters, until the flux drops out of their filter band. So surveys like the dark energy survey are going to be very complete out to about redshift 1, but they suffer from the problem that there's a large scatter between their observable proxy, the number of galaxies in a cluster, and the mass of the cluster, which limits their cosmological constraints, or currently limits them. On the other hand, X-ray surveys, such as reflex, the XXL, and to be launched next year, this wonderful new satellite by the Germans, eROSITA, X-ray flux gets fainter the further away you are. They suffer from cosmological dimming. So for a fixed sensitivity, you only can find clusters at higher mass as you go out to higher redshifts. On the other hand, SE surveys, such as those done by the South Pole Telescope, by the Atacama Cosmology Telescope, with high-resolution observations of the cosmic microwave background, we can find a mass-limited sample of clusters out to the highest redshifts of which clusters are formed. We have found the best way to find clusters into the distant universe with the mass sensitivity simply set by the instrumental noise, currently to date. And in this talk, I'll be really highlighting work we've done with the South Pole Telescope and bringing in how these actually are very complementary. Clusters are really multi-wavelength probes. They're full of gas, they're full of galaxies. We want to use all of these tools together to better understand our systematics, to best constrain cosmology. And so I'll also be mentioning work we're doing with the Dark Energy Survey, which is a wide area optical survey. So this SZ stuff I've been talking about, Tsarnaev-Zeldovich effect, is a long predicted effect by Tsarnaev and Zeldovich, and it's actually quite simple. So you have this hundreds of million dollar Kelvin gas trapped in these deep gravitational potential wells, and about 1% of the microwave background photons come in. They inverse Compton scatter, get a kick in energy, and are blue shifted. So what this does to your beautiful 2.73 Kelvin CMB spectrum is it distorts it to higher energy. And so now if you subtract off this initial blackbody spectrum, what you'll see is a deficit of photons at lower frequencies, a null at 220, and an increment at higher frequencies. This is a really characteristic signature to see a dark spot at low frequencies and a hot spot at higher frequencies on Archimedes scales. Think about radio galaxies and their other sources. They're sources of emission, not decrements, not holes in the sky. This is a really nice characteristic feature of SC clusters. And because of the scattering process, it's redshift independent, which enables us to detect these out to as high a redshift as clusters have formed. The other critical thing is that this observable, if you notice here, this is what we observe, NEKT, is proportional to the thermal pressure in these systems, and that's tightly coupled to the mass of these systems. So the integrated signal is proportional to thermal energy. It's a low scatter proxy for the cluster mass, about 5 to 6% if we can measure YSC perfectly, and about 18% when you fold through all of the SPT characteristics, which I'll talk about. And this is why high-resolution CMB experiments, such as done by SPT, by ACT, in the future by SO and CMBS4, are fantastic. Because in the history of the universe, the entire universe is imprinted upon this cosmic microwave background. From the earliest signals from inflation, which manifest themselves as B modes, B mode polarization in the cosmic microwave background, this beautiful picture we now have of the microwave background at 400,000 years after the Big Bang, the CMB photons traveling through us, getting gravitationally lensed by galaxies and clusters of galaxies, and finally, the cold spots imprinted by clusters in the lower redshift universe. And we're in a really exciting time because not only do we have these fantastic high-resolution CMB experiments taking off, but we also are coming in an age for optical astronomy. We're going to have these wonderful wide-area cluster surveys. Currently, we have Dark Energy Survey. The future in the next early 2020s, the billion-dollar LSST project will be turning on, which is going to make tremendous advances in optical survey astronomy. And then spectroscopic, wide-area spectroscopic surveys, such as DESI. So the South Pole Telescope, it's very impressive, actually. Ignore these three people, though that's me for scale. Has had 3 generations of cameras. So the primary stuff I'm going to be talking about today are SPT-SC and SPT-Pole. The 10-meter dish gives you an arc-minute resolution on the sky, roughly the resolution of the human eye. And we've nestled our bands, our detection bands, into the nice atmospheric window. So we observe with SPT-SC at 90, 150, and 220 gigahertz. With SPT-Pole, we added polarization, and it's a 2-channel camera at 90, 150. And our newly deployed SPT-3G camera with over an order of magnitude more detectors added, again, a 220 channel, as well as polarization sensitivity. Now, the work I'm telling you about today is not just my own work, of course, but it's the work of the whole SPT collaboration, a number of people shown here. So you build this great telescope, you assemble this great team, And then, you fly in and you're stuck at the South Pole for 9 months. And this is what we do. So this is the South Pole telescope observing during the winter. And we're looking for winter overs, by the way. If you're interested in seeing this view in real life, come talk to me or Tyler or Matt after the talk. But what we do is we simply scan back and forth. You might notice the sky just rotates. We're at the South Pole, so we just scan the same field over and over again, thousands of times for the SBT pole experiment. Robert Schwartz, who's a BICEP winner, actually took this photo. And the first survey we did this, we split this 16th of the sky into 19 patches and observed these to depths of 40, 17, and 80 microkelvin arc minute. So that's the full CMB survey. And this is now comparing our data to Planck, the all-sky survey. So this is about 50 square degrees at 143 gigahertz from Planck, which was 2 times finer resolution than the leading WMAP survey at the time, and 7 times deeper. Now, if you fold in SBT, just like to flip back and forth here, this is what going from 5 arc minutes to arc minute resolution buys you. I hope you notice there's a few important features that start popping out in these maps. Now, if we high-pass filter this data to really accentuate the small scales, we do still have some residual CMB anisotropies, both primary and secondary anisotropies of the CMB. There's these really bright point sources, which are usually AGN, accretion disks around black holes. Once in a great while, about 80 over the whole 2,500 square degrees, we get a highly gravitationally lensed star-forming galaxies, which Redshift 3, 4, 5, 6. And then the thing that I work on, which makes me excited in these maps, are these cold spots, these shadows in the CMB sky. These are clusters of galaxies, as discovered by the South Pole telescope. Now, I'm an CMB experimentalist. One of the most powerful tools in our toolbox is hitting these and measuring the power spectrum. There's a wealth of information encoded in the power spectrum of the CMB, from the largest scales, which encodes the primary cosmic microwave background, which Planck has really nailed, sort of basic lambda CDM cosmological parameters with some interesting tensions, perhaps, between constraints inferred from the lowest and higher angular scales. And then coming out here, everything else. So we observe with 3 frequencies, and encoded in this data set is a wealth of information about both cosmology and astrophysics. And if you split this into multiple components, we have maps at all 3 frequencies. You can take auto and cross spectra, and you can tease out from these contributions both the primary CMB, you see the damping tail here, the power spectrum from clusters of galaxies, from radio sources, which are brighter at 90 gigahertz and falling and essentially very faint at 220, versus dusty sources with, of course, a rising spectrum, more power, 220 gigahertz. And with this data set, we can place tight constraints on astrophysical models. If we knew exactly how to model the gas in clusters exceedingly well, we can place constraints on cosmological parameters such as sigma 8 to about 0.5%. However, we don't know gastrophysics that well, and instead what you can do with these data sets is turn around and flip it and say, this is the constraints that you must have when you run your hydrodynamic simulations, when you run your large simulations for what the gas in these objects is doing. Now, one important thing we'd like to do is to connect measurements from Planck. This is now measuring the power spectrum from clusters, the Y map, Compton Y. It's a function of angular scales. This is what Planck has measured out to about 10 arc minutes, which is where they smooth their maps to. And then this is where SBT and ACT have measured this SC signal. Now, these might look rather discrepant. They're not. It's about 1.5 sigma because these Planck error bars are highly correlated. But it would be really nice to be able to connect the whole model from large to small scales and show that everything is completely consistent. And this is something we're working on. So we're working to combine, instead of doing this in cross-spectrum space, to actually combine the 3 frequency maps to pull out and isolate this Compton Y, this SC signal, to be able to probe from large to small scales and better constrain these models. Also for cross-correlation, so you take your favorite galaxy sample, or your favorite cluster sample, and learn about large-scale structure, Compton Y, TSC cross-correlations, the gas in those systems. Cluster pressure profiles, feedback, how clusters and lensing cross TSC. So this is just in progress. This is 16 square degrees out of the 2,500 square degrees. And you can see it's rather noisy. So this is one of the most extreme clusters in the whole universe. It's called El Gordo, the fat one, which was discovered both by ACT and SPT. And it's a 40 sigma detection in the SPT map. It's over 10 to the 15 times the mass of the sun. But it's really, there it is in this Y map. We're really limited on signal to noise on individual objects right now, and where the real gains is going to come is from stacking and from cross-correlating survey data from DES and SPT. So this is coming. Stay tuned. But what the rest of my talk is going to be about is not the aggregate cluster population in the SPT maps, but rather the individual high signal to noise ones we managed to find. And so we use what's pretty standard techniques in electrical engineering for LIGO, for other template-based techniques, where we apply a multi-frequency match filter technique to identify clusters of galaxies. So we have this decrement and this null at 220 gigahertz. We know the frequencies, the effect of SD clusters. We know what their Fourier space shape looks like, what their profile looks like. You can feed this in to a multi-frequency match filter, optimally combine these three frequency bands, and isolate the SPT signal, the cluster signal. In practice, this has been challenging. People looked for these ST decrements for decades, but the first blind detection actually happened by SPT in 2008. The instruments finally reached the requisite sensitivity to detect these clusters. So in this top row, I'm showing you the raw CMB data without this multi-frequency filter applied. Then applying a filter to each individual channel. You can see, especially this one, it filters away that primary CMB and leaves you with the decrement and then the null at 220 gigahertz. Just to emphasize, these are 200 microkelvin fluctuations sitting on top of the 2.73 Kelvin blackbody. So an incredibly small signals we pull out. So we don't just have 4 clusters these days. For the first survey, we identified over 677 candidates from this initial survey in the SPTSC sample. And looking at this, I could not tell you their redshift. That's part of the cluster cosmology, is you need to know where they are, not just find them, but know where they are. So in order to identify their redshifts, we followed every single one of these candidates up with optical telescopes to identify the galaxy counterparts to get their redshifts. Ranging from the 1 meter SWOPE telescope, which I was very happy, having spent 2 months observing with SWOPE, to see was in the LIGO detection papers. I think that's a wonderful telescope. Up to the high redshift using NASA space-based facilities to find our highest redshift clusters. So this was the result. So this is now, of course, for a fixed cosmology. But this is the black points are the SPTSC survey, really illustrating the mass-independent selection. In fact, a slight downturn because our noise is a little bit better behaved at smaller scales of a high-resolution SD cluster survey. But this is, of course, a bit of a cheat. So the redshift is great. We fix the cosmology to get these masses, but we don't want to fix cosmology. We want to constrain cosmology with clusters. And so in order to do that, we need to measure masses. And this is the fundamental limiting systematic these days in cluster cosmology, is what are the masses connected to these observables? Whether you're counting galaxies, whether you're measuring the signal to noise of these shadows in the CMB sky, or the temperature you would measure in an X-ray observation of the clusters. And to tackle this, we're not just going at it with one hand, we're going after it with a broad multi-wavelength mass calibration campaign that includes building off of 30 years of work in the X-ray community, using observations from Chandra with an XBP program led by Brad Benson and extended by Mike McDonald to the highest redshift clusters. We're using weak lensing data, both external, using this X-ray calibration, as well as our own internal data using the 6.5 meter Magellan telescopes for sort of moderate redshifts, and then HST for the highest redshift systems. And then finally, using dynamical masses, using the galaxies themselves as test probes of the gravitational potential well to get velocity dispersion-based masses, using both data from Gemini, VLT, and Magellan. So roughly about a third of our SPT sample has not photometric redshifts, but spectroscopic redshifts, including a paper which is coming very soon, which I'm excited about. I'm working on a grad student at Chicago with Matt Bayless and Mike Gladders and others, Gaurav Keeler, where we confirmed the 5 highest clusters spectroscopically using deep integrations with the LDSS3 camera at Magellan. So to get cosmology out of this, we do what's pretty standard in the field. We use a Markov chain Monte Carlo method, where we simultaneously vary the cosmological parameters we're interested in, along with this mass observable relation in a self-consistent way. So in order to relate the signal to noise of the SPT clusters to overall masses, using the X-ray data, we fit for a normalization, a slope, a redshift evolution term, scatter between the SC signal and mass, as well as correlated scatter between the X-ray and SC observables. The cosmological parameters we fit, we test for a base lambda CDM cosmology, and then we add extensions for WCDM, neutrino masses, etc. Where these normalizations, the prior in the normalization is effectively set by our weak lensing calibration. The slope is set by previous measurements based on a prior of Vauquelin 09, Hoekstra 15. Redshift evolution, we set a prior of self-similar evolution, but we also add uncertainty. We're discovering the high redshift cluster population is really discovery space. SC surveys are finding tens to hundreds of these clusters now, and so we're really learning a lot about the cluster population at redshift 1. So we add an additional 10% uncertainty to our mass calibration. Finally, we have priors on scatter as well. And this is the result. So this has been a long slog from our first cluster cosmology paper in 2013 using 21 clusters, which Keith actually wrote. Vanderlyn here wrote the detection paper from. Then adding an evolution to 100 clusters, and then finally this full sample of 356 clusters. Whereas we've added more clusters, we've shrunk in this direction, and the uncertainty contours in this direction are really set by our systematic uncertainties in our mass calibration. So we've decreased the area in the likelihood space by about a factor of 4, going from 21 to 356 clusters. However, there's still a lot we're learning about systematics and clusters. I mentioned it's a systematics limited game, and there's been a substantial improvement since the initial Vauquelin 09 mass calibration to understanding of how to calibrate the weak lensing observables in clusters. And so this has shifted our mass calibration by about 10% relative to this initial calibration, primarily being driven both in the weeds for weak lensing a little, but by measuring the multiplicative bias for those who work in this area of the shear, by making simulations populate with fainter galaxies, as well as adding infrared data to improve the fidelity of the photometric redshifts for the background sources. So this whole data set was really limited now by the small sample of clusters, which we're using this external prior for the YX weak lensing mass calibration we're tying to. The next step is to both increase our cluster sample size to shrink these contours more and extend our lensing sample and extend it to higher redshift. And that's really, yeah.
Some BBN.
Sorry, what?
So there's a BBN prior on.
Yeah, it doesn't really change that much. We just put it into the Cosmo chains. We can't constrain it. Okay, so the next step in our process is to do lensing, and more lensing. It's all about mass calibration. It's all about grinding down that uncertainty and doing systematic cross-checks. And for us, that's a three-pronged approach. Low redshift using this wide area optical survey, the dark energy survey that covers the SPT footprint. At modest redshifts, we're doing deep data from Magellan Megacam. And then finally, we have a high redshift program with the Hubble Space Telescope. And one new exciting area in the field, which is really starting to take off, is using the lensing of the cosmic wave background itself to calibrate the mass of these clusters. Thus far, individual detections in the optical weak lensing regime are quite high significance, and stacking the entire SPT sample for CME lensing gets you something like a 5 sigma significance. So we can do 5 sigma or more on individual clusters with optical techniques. CME lensing is growing in power, but it's particularly useful at higher redshifts where you run out of background sources for the optical weak lensing. So this is going to be an incredibly powerful probe moving forward, but it's just getting rolling today. So for our HST Megacam sample, we just published this past year the first steps in this program. So we have 19 clusters observed with the 6.5 meter Magellan Telescope Megacam. And as well as about a baker's dozen observed with the Hubble Space Telescope pushing higher redshift. Just showing here, this is all of the clusters observed for weak lensing with HST. This G et al. Paper is basically a grab bag of what was available. SBT has created the highest redshift uniform selected weak lensing calibration sample for clusters. And when you fold that all through and you do this internal weak lensing, compare it to our external priors, we're happy to say that they're completely consistent. This was actually very nice to see, that the results of this weak lensing calibration in a paper by Dietrich et al. That came out last fall show that our priors on the amplitude, which is our current limitation in those contours, is completely consistent with the previous results, tying through the X-ray calibration. And I wish I had a little bit more to show you. We're hot off the press doing the internal weak lensing calibration cosmological results from SBT. So Sebastian Bouquet just sent me this plot this week. He's busy running chains at Argonne. But this is now showing for SBT clusters alone, compared to KIDS, this wide area weak lensing survey, to Planck, to Weighing the Giants, which is another very competitive X-ray survey, the SBT contours. So we're really starting to hone in on this space, and we're currently completely consistent with these other cosmological probes. The chains are running to open the box to WCDM, because that's what's really interesting. It's not just sigma 8 omega matter, which clusters constrain well, but clusters break degeneracies and other data sets to help place interesting constraints on W and neutrino masses, and those chains are running. So that was SBT-SC. We've, of course, kept going with the SPT pole survey, which was deployed right after SPT-SC, with 3 surveys. So there's a small first survey at 100 square degrees, which is at depths of roughly 5 and 3.5 microkelvin arc minute when you combine all the data. The workhorse of this survey is SPT pole, this 500 square degree patch here, which also nicely lies in the bicep field, which has reached depths of 12 and 5 micro-K arc minute, just to compare to the initial SPT-SC survey. And I love this plot. So this is from a paper by Jason Henning. This is now the SPT pole 500 square degree field and temperature, Q, and U. So you're seeing this polarization of the CMB by I. You notice the vertical and the crosshatch patterns. This is the E-mode polarization of the cosmic microwave background, which I think is pretty fantastic considering a decade ago we just had faint statistical detections. Now your eye is detecting these E-modes. And so if you put this on a power spectrum plot, now this is comparing both Planck, ACT, SBT, and SBT pole. This is what you see for the temperature, the E mode, and then the lensing B mode constraints from SBT. But this talk is not about that, though this is such a beautiful result, I have to show it. This talk is about clusters. So one of the really wonderful things now is that we have this great overlap with the dark energy survey. So the dark energy survey is this Starship Enterprise shaped thing here in the background. It's 5,000 square degrees. It was coordinated to overlap with the SPT surveys. So it's a deep optical survey, GRIZY bands. It will detect on its own about 100,000 clusters out to redshift 1. Its key areas are a cluster survey, weak lensing, BAO, and they have dedicated supernova fields. And with this coordination of SBT, we have both our main SBT-SC footprint, the 500 square degree, and this new extended survey to the north, where SBT has now observed 5,000 square degrees with our summer field data, what we call our summer field data as we observed it in the austral summer. So no longer do we have to go and sit in telescope domes and point and observe clusters. DES just gives them for free when we overlap. So from low to high redshift, we can pick them out. And the catalog construction is well underway. So this is now incorporating all of the SPT pole data. The mapped depths are about 5 microkelvin arc minute, so much deeper than SPT-SC. Using DES data, you can see that the lower noise has pushed down our mass threshold, pushing us up to higher redshift. Showing down here, this goes up to redshift 1.4. Where this missing area here is not that there's not clusters. We're busy analyzing infrared data from 2 completed Spitzer programs, and I was very excited that the Spitzer Cycle 14 program was just approved to keep finding these high redshift clusters. And with this overlap data, can not only do this cluster census, we can cross-check each other. Cluster cosmology is systematics limited. It's important to make sure that we understand the SC selection and that we understand the optical selection from DES. That the richness, the number of galaxies they count, is consistent with the mass you would predict from SPT. That our masses are consistent with what DES measures from weak lensing. And so this is early work we've done led by Alex Saro in this sort of science verification footprint, a small, roughly 200 square degree footprint, just comparing cluster observables to see that the richness and the mass of the clusters is generally consistent with expectations, which is good. It's actually great because some of the earlier work from Sloan and comparing Planck and Sloan showed this was not the case for those earlier surveys. And finally, it's also critical for weak lensing calibration that when you're calibrating things in radii around a cluster, you need to know where to drop your aperture. So you need to know where the center of the halo is, the dark matter halo, versus what your center proxy is. So for optical surveys, you use the brightest cluster galaxy. For SC, we use the gas center. And these should all be related. And understanding the two shows that there really are two different populations of clusters, a nice, well-centered, relaxed cluster population, and then where are these offsets, such as things like the bullet cluster, where there are mergers in the clusters that separate the two. Finally, something which is so close, I'm very busy reducing and analyzing this data, is this extended survey, the SPT Pulse Summer Survey, which covered 2,500 square degrees to the north. We have something like another 500 SPT clusters detected in this region. Work is ongoing to finalize the map cuts, finalize the cluster selection, finalize the optical calibrations for the follow-up data. But it's also sort of fun when you look at new surveys, as I was looking through this data, just to see what we see in the CMB maps. So the CMB maps I showed you before were sort of blobby, featureless things with a few specks. But once in a while in these surveys, we pick out things like NGC 0055. You can just see the dust emission from this galaxy, or the Sculptor galaxy, brighter dust at 150 than 90 gigahertz, and the Orion, the Helix Nebula in the CMB data. So when I saw that, I thought the focal plane had glitched, but then I looked at the coordinates, and that was pretty exciting that we actually see sources, extended sources in our map, which I quickly masked and moved on. But when you find lots of massive clusters, you can do a lot more interesting things than just count them. So one of the other big projects I'm involved in is using these clusters, using the fact that they are the most massive systems in the universe. That makes these systems potentially very efficient gravitational lenses. And with this mass limit selection, we can now measure the lensing, the strong lensing properties, where you get these multiple arcs and features. I hope you can see these with the screen, out to high redshift. And this is also a really compelling science area because strong lensing provides direct tests of structure formation. I mentioned that we have to connect our observations to simulations. We connect them through these complex, large n-body simulations, which provide predictions for the number of clusters as a function of mass for different cosmologies. This is sort of the underpinning of how we get cosmological constraints from clusters. But they also make predictions for the properties of dark matter halos, and they better be consistent. So this is one way we can test the consistency between cosmological simulations and our observations, is by measuring the cores of these massive gravitational bound systems. And so what's shown here, and this is a recent paper by Hilary Child, who's a grad student in our Argonne group, is now from this very large volume outer rim simulation, the mass versus concentration, how concentrated the matter is in these clusters, compared to existing constraints from the large HST clash program. With this sort of concentration measurement, you can get better modeling for masses of clusters. And when you identify these strong lenses, they also are a powerful magnifying glass. They're greatly magnifying the flux from background sources. And so once in a while, you will get a rare source from the very early universe, potentially enabling you to probe reionization. With time delay astronomy, you can do things like measure the expansion rate of the universe. There was a really exciting paper that came out from the first one of these last year. And then finally, you can do things not in the optical, but with those strongly gravitationally lensed dusty sources I mentioned earlier to measure the substructure using high resolution observations from SPT sources with ALMA. To tackle what we wanted to do this program, we've undertaken a large imaging campaign using the Magellan Pisco imager. So we've got uniform coverage of the SPTSC sample as well as the extended cluster survey sample using a new camera, a relatively new camera on Magellan called Pisco, which is really a cool idea. It's got simultaneous imaging, GRIZ, at the exact same time in a 5 by arcminute field of view of whatever you pointed at. We've adapted the exposure strategy to compensate for the telescope air mass, the local conditions, the seeing, the lunar brightness, and optimizing the Magellan observing. We were able to observe up to 120 clusters in a good night. Now, it's not enough to just identify the strong lenses. You need the geometry as well. And so we've also had a large spectroscopic campaign targeting all the strong lenses we've seen so far, which is still ongoing, follow-up campaign. Thus far, we've observed over 450 clusters with Magellan Pisco and better seeing. 0.9 is an upper limit, most of them are around 0.7. Another 130 have HST or Magellan Megacam data as well. And just to show you the difference, this is our confirmation imaging. I hope you can all see there's an overdensity of galaxies, which was good enough for getting a redshift. And this is now the same cluster with 300 seconds of Pisco. And it just reveals the rich data set of multi-lens images, which can be used for these studies. Now, in order to connect what we're doing with these observations to models, we have to connect these to simulations. So one of these clusters is a simulated cluster, and one of these clusters is a real cluster. Raise your hand if you think it's the one on the right is a real cluster. What about the left? All right, so this is actually the real cluster. This is the real SPT cluster. And this is a simulated cluster, which in a paper read by Nan Lee et al., which Nan and I and others at Argonne and Mike Ladders have folded through to mock up realistic clusters from these large N-body simulations. We don't going to talk through the details here. Needless to say, you identify all the clusters in this outer rim simulation. You ray trace the whole thing with multiple plane ray tracing. You process and you pin on things that look like the real observational data. So we've analyzed the Pisco data and its artifact to really make the mock observations look as realistic as we can. So here's an example of lensing the Hubble Ultra Deep Field, adding cluster galaxies, convolving with a PSF, and adding artifacts and camera instrumental noise. So this is work that's very much ongoing. But what we hope to do, what we have already seen actually, is we've identified something like 150 new strong lenses in the SPT sample with this reasonable ground-based seeing. This is the redshift distribution we're expecting for that. I could update it. We're still in the process of finalizing the Pisco data to make the reductions as good as possible. But with this process, what we hope to do is measure this mass concentration relation of massive clusters to about 5%, constrain its scatter to about 10%, and for the first time ever, be able to measure its redshift evolution, which come from direct predictions and comparisons to simulations. So one question I always get is, well, okay, great. These are dark matter simulations. Maybe they're a little too cuspy. We know things go on in the cores of clusters. And this is something I'm very excited about that's coming on now. So J.D. Emberson, of course, was at CITA. He's now a postdoc at Argonne. J.D. and Nick have been working hard to implement hydro into the Argonne simulation framework. So this is a beautiful picture from their test cluster case with Santa Barbara, where here's the cold dark matter and the baryonic matter. But they just finished a simulation called the Borg cube, which is 800 MPC over H, full hydro, which we will run through this process and be able to directly compare the statistics we see with hydro, and then in the future with different feedback simulations to this observational data set we're constructing. So what's next? Well, all CMB experimentalists show this slide, so I'll show it too. CMB detectors have been essentially background limited since Akbar. So the only way to get more sensitive is to go bigger. And so that's what the field has done with SPT. We had 1,000 detectors, 1,600 with polarization of SPT pole, order of magnitude more with SPT 3G. And finally, CMB stage 4 is proposing to put 100,000 detectors on the sky to really increase our sensitivity to measurements of the cosmic ray background and all of this wonderful intervening structure. At the same time, Optical telescopes have been scaling up too. So we're getting this rich multi-wavelength data set from Sloan to the Dark Energy Survey to LSST, which should turn on in 2021. It's just going to be phenomenal for survey science. So for SPT3G, this is what we're predicting. So this is SPT-SZ. We're going to significantly push down the mass threshold of clusters. When you push down the mass threshold, of course, you probe to higher redshift, clusters form. So as you can push lower, you can probe more high redshift systems with over 1,000 systems above redshift 1. So right now with SPT-SZ, we've found 37. Above redshift half, we more than doubled the number of massive clusters known. With SPT3G, it's just going to blow this out of the water. With this data set, you can use that lensing of the cosmic microwave background itself to help constrain the mass calibration of your clusters. Stacking all of these just SPT clusters should get you something like a 30 sigma detection of mass. And if you restrict that to above redshift 1, we should still be at about 10%. So it's going to be great for constraining the redshift evolution, our mass relations. And finally, for cross-correlation science, with these 3 channels, we should make really wonderful high-resolution Y-maps of the cosmic from this data set for cross-correlation science. So just to summarize here and say that we found hundreds of massive clusters, spanning a redshift range of about 0.5 to 1.7 is our highest spectroscopically confirmed cluster to date. This sample has led to a fantastic sample for cosmological and astrophysics studies. So far, our cosmological analysis has been consistent with other cluster surveys, as well as measurements from cosmic microwave background cosmology. Better mass calibration is always needed for cluster cosmology to tighten these constraints, and work is ongoing. With this strong lensing program, we're going to find something like 150 to 175 clusters. This will place constraints on the mass concentration relation, be a very important test for simulations, and will allow us to really probe the cores of clusters. And finally, SPT3G is deployed and observing, and we're really excited for the data sets that this is going to produce. Thank you.
Thanks so much for listening.
So, what extent are high redshift cluster counts now constraining cosmological non-Gaussian energy?
So, let me see if I can figure out how to go through this. Right. So that was a really interesting thing that people were looking at.
It's an old question.
It's an old question, exactly. So what's shown in this plot is the exclusion region. So if you find anything here, you break lambda CDM, basically, as we know it with FNL. So FNL constraints from clusters aren't so great. So with the first, in 2011, we wrote a paper looking at sort of studying the most massive clusters in the SPT sample. We just did a shallow survey and picked them all off. And it was a few hundred. So in order to really push FNL, I think you're going to need approaches like the proposed Spherix mission.
So
I think so.
Redshifts 2 to really start.
Right, but then I start getting worried about selection. I mean, this is discovery space for CMB surveys. And one thing I could show on the backup slides, but I didn't mention this talk to not go into the weeds, but we know there's CIB in these clusters. We know that star formation is picking up as you go to redshift 2. We know that even in the spectroscopically confirmed sample we're seeing with SPT, we're starting to see increased O2 emission, which means that the CIB is going to start filling in the decrements. But then we have this multi-frequency coverage. So it's going to be an exploration to understand how well we really are able to pick off these high redshift clusters. Undoubtedly, it's going to blow up the scatter in our selection and make our mass calibration more uncertain.
And even Rosita isn't sensitive enough.
No, this is the 50 count threshold bar for E-Rosita. So it's, the other problem is how are we going to confirm those clusters at redshift 2? So 50 counts is not enough to get an iron line from X-ray. There will be things like W-first and E-Rosita, which will help. Whether they're able to push that high is, we'll have to see.
When you find so many clusters, is there a point when you could measure the clustering?
Yeah. So SPT3G will be on the verge. So that's a great question. You need about 10,000 clusters in our footprint. Is about the right number to start seeing a clustering signal.
Over which footprint is that?
About 2,500 square degrees would have done it. So SVT 3G will, in 1500 square degrees, sorry, I'm not good at advancing these slides. We're going to have, depending on your cuts, we can cut a different signal to noise, 5,000, 6,000. But one of the interesting things we're actually starting to play with is you don't have to cluster with just SVT clusters. You can cluster with SVT cross DES clusters. So that work is starting to go forward.
Or anything, right?
Or anything, right. So you can red magic galaxy, LRG galaxies. Galaxies.
Do you have any cross correlation signal in the catalog that exists today?
Yes.
For sound tracer?
Yes. The DES has this wonderful, by Eli Rykoff and Eduardo Rosso, they've created sort of like a CMAS-like sample out of the dark energy survey of luminous red galaxies, and they call it red magic. And that covers the full DES footprint. And so in principle, one of the things we'd like to do, there are so many great projects and so few people, is to actually measure this clustering of SVT clusters with this red magic cluster sample.
I was wondering how dependent is the match filter? I mean, is it really just a convolved point source, or is it?
It's a.
We were looking at it kind of looked blobby.
Yeah, that's a great question. So I don't even know if I need to show you or I could just talk through it. So we don't use a point source because that would be the beam. When we want to find point sources, our match filter is our beam. But for clusters, we use a beta profile. We're not sensitive whether you choose an RNO or a beta profile. And we use a grid of scale. So we do a quarter arc-minute to a 3 arc-minute beta profile. And we maximize the signal to noise. And debiasing that maximization is one of the steps in the mass calibration. So it does matter. So for very low redshift clusters at like 0.3, they often peak at 3 arc-minute beta filters, 0.2. And then as you go to higher redshift, they're all pretty much uniformly quarter arc-minute small in the scale. But it's actually, I don't have this plot in this talk, but it's actually, if you do signal to noise versus filter scale, once you get about redshift to half, there's a mild peak, but it's generally pretty flat.
So yeah, so I guess my question was if there's kind of a possibility for finding things at intermediate redshift and not that might not that might not be. That could have some weird morphologies.
Yeah, so the scales, you would expect those weird morphologies. We're pretty blobby, so it generally washes out. So that's a plus and a minus, but we generally wash out the cores of the clusters. So we don't tend to be sensitive to that. And we can check that on simulations and have. So that was a question that came up with Planck, actually, maybe going a little bit astray. But there was a question, do SC surveys tend to find more mergers? And there was a nice paper led by a student, Danyar, with Mike McDonald, which showed that no, the fraction of mergers versus non-mergers is essentially consistent with what you'd expect.
So for the richest clusters, they said maps we need to pick out the filaments feeding the clusters?
So that's one of the things we'd like to do with these Y maps. And for some of the Planck clusters, they're saying they might be seeing signs of a filament. But that is, I think, one of the hopes for future Y maps is to actually be able to see this filamentary structure. And we could perhaps detect it in cross-correlation right now. But not yet.
So it sounds like you just need a big enough sample to pick out the outliers, which are the most spectacular cases.
Yeah, and we need deeper data. So the combination,